Hey guys, welcome to this free lesson on concavity and the second derivative test for concavity. Just a reminder, the way that these videos work, you want to pause and try the examples, and there are free guided notes available. In this video, we're going to talk more about theory. I have another video where we'll look more at examples, so we should have you totally covered on this topic when you're done. And hey, if you want to do me a solid, consider giving my video a like, subscribing to my channel, or sharing it with your friends if you find it helpful and they need calculus help too, or leave me a comment. What's going well, what's not going well. My goal is to provide as much free math help on the internet as I possibly can as a one-woman shop. Okay, so let's talk about this. We're talking about concavity, right? So the idea behind this is, well, first things first, let me just draw two graphs here. You probably have a little bit of an intuitive sense of this. Is this graph, do you think that this graph is concave up or concave down? This one is concave down. And what about this other one? Is this concave up or concave down? Well, by process of elimination, it would be concave up. So this is what we're going to be discussing today, this idea of concavity, and then we're also going to take a look at this other situation where, let's say I have a graph that works something like this. Okay, well, you know that this is concave down and this is concave up, and if you look at this graph, you can visualize there is a point where the concavity starts to change. So just take a second and see, can you kind of in the back of your mind just determine where that point is? It's somewhere around here where concavity changes. This point is called an inflection point, so we're going to define all of this today. So now let's talk about some definitions here. First, this is the definition of concave up and concave down. I would recommend pausing the video to write these down. For a differentiable function f of x, the function is concave up on an open interval if f prime of x is increasing on I. Another word for this is convex. Convex and concave up, they mean the same thing. And then we also have concave down. A function is concave down on an open interval I if f prime of x is decreasing on I. Okay, so this is one way that we think about concavity, and it has to do with the behavior now of f prime of x, so the first derivative. Although a lot of times when people think about this, they think of the second derivative. So let me just present to you then the second derivative test for concavity. All right, so I would once again recommend that you pause the video and write this down, and I'll read this out to you. Let f of x be twice differentiable on some interval I. Then, if f double prime of x is greater than 0, i.e. if it's positive on that interval, the graph is concave up. If f double prime of x is less than 0, i.e. if the second derivative is negative on that interval, then the graph is concave down. I think a lot of times this is how people really think of concavity. They think more of with the second derivative. And so we're going to explore this a whole bunch today. In some ways, this should feel very similar to the first derivative test. In fact, I would recommend that you just flip back in your notes and look at the first derivative test and compare the language of that test to this test. It's very, very similar, but now the second derivative generally has to do with concavity. That's kind of the difference between the first and the second derivative in some ways, although there is another plot twist to that, but that'll be for another video. Okay, so the other thing is, what do we have when concavity changes? That is exactly what I was talking about with this little idea here. So concavity is changing from down to up. What is this? This is called an inflection point. Inflection point, point of inflection, tomato, tomato, whichever way you want to call it, you get the picture. Okay, so how do you find inflection points? So this is, again, very similar to what we do with first derivatives and finding critical points, except now we're doing everything with the second derivative. So to find inflection points, what you want to do is you want to look for where f double prime of x is equal to 0, or where f double prime fails to exist. Again, feels very similar to what we do with critical points, right? So, and for an inflection point, if the concavity changes at that point, then you have an inflection point. So this will look and feel very, very similar to what you do with the first derivative and critical points, except now we're dealing with the second derivative and inflection points. Okay, so the first thing I want to do here is just make sure we have this nice intuitive understanding of this. So I have these two graphs here, and this is not meant to be something super precise, but I just want you to take a moment to draw these graphs on your own. And just where do you feel like the point of inflection is? So where are the points of inflection? So go ahead and draw these, pause the video, mark it, hit play when you want to see the answer. Okay, so Here I've got my graph is concave down and then it switches to concave up. So I kind of feel like the point of inflection would be probably somewhere around here, right? You can see that it's kind of being cut off. Now here I'm going from concave up, concave down, concave up. So where does this change? I'd say somewhere around here. Let's see, I'll make that nice and big for you guys. And then probably also somewhere around here. So it doesn't have to be perfect, but you kind of get the idea. So that's just checking that you have this nice intuitive understanding of a point of inflection. Okay, so now I'm going to show you guys one example, and in the next video I'll have even more examples if you'd like to see them. In these examples, what I want to do is I want to determine where the graph is concave up or concave down, and then I want to find, well, let me change the directions on this. We want to find where the graph is concave up or concave down, and then any points of inflection. Okay, so here's the example that I'm going to work with. So obviously concavity has to do with the second derivative, so why don't you pause the video and go ahead and find the first and second derivative, hit play when you're ready. Okay, so let me write this out. So there's my second derivative. So now what I want to do is I actually want to start by finding my points of inflection. So this is a polynomial, the domain is all real numbers, and there won't be any places where this second derivative fails to exist, so I don't have to worry about that. So instead I just have to set it equal to 0. So if I set it equal to 0 and solve, x is 1/2. All right, now here's the part that's going to feel very similar to what you do with the first derivative test. So I once again want to actually make some intervals, and I'm going to make the intervals around the domain. Once again, I'll just remind you that the domain is all real numbers. And now I'm basically going to split up this domain now according to this potential inflection point. So let's set up a table. This table looks very familiar to what we talked about in the first derivative test. And by the way, if you don't know what the first derivative test is, I will go ahead and leave a link in the description of this video if you need to go back and watch that. Okay, so now I'm just going to break up this with this potential inflection point. So my two intervals, in a very similar manner of what I would have done with the first derivative test, I'll just kind of break it up around this potential inflection point. And now what I need to do is I need to figure out what is the sign of f double prime. So just like we did before, you're going to use a test point. And if I use something, so for this first interval, let's say I choose x equals 0. Okay, so I now want to plug x equals 0 into my second derivative. And all I really care about here is whether or not this is positive or negative. I've talked about this at length, but you can go ahead and evaluate this, but most of the time you really don't need to. The thing that you're really interested in here is just, is this greater than or less than 0? So this is less than 0. So the sign of this is negative, so I'm going to note that in my table. Should feel, again, very familiar. Then if I choose another test point here, so let's say that I choose something like x equals 1, well, now I evaluate this for f double prime of 1. And again, I could go ahead and actually evaluate that, but the answer doesn't really matter. The only thing that I'm really trying to figure out is what is the sign here, and this ends up being positive. Okay, so now we can draw some conclusions. First of all, we know our intervals for concavity, right? So let's go ahead and summarize that. So I'll clear some space, and I'll go ahead and summarize. Okay, so there's my concave up and concave down. Should feel very familiar to working with increasing and decreasing intervals. Next, let's talk about points of inflection. So let me clear some space again. And similar to how we view critical points and then we kind of investigate the increasing, decreasing intervals around them, now we do a similar thing with concavity. So all you're looking for now for a point of inflection is if the concavity changes. So in this case, I'm going from negative to positive, therefore the concavity changes. So therefore, 1/2 is an inflection point. So what this means is f of x has an inflection point at x equals 1/2. Okay, so in the next video, I'm going to look at some slightly more difficult examples. This is just kind of the basics. So if you want to see some more examples, I'll see you in the next video. And otherwise, divide and conquer your math, guys. I'll see you next time.